Okay, we are ready for our last talk. And congratulations, you all almost made it. So we were talking, well, it was talking about the very, very low-level shading and GPU details and all that, which was awesome. And now we're going to lift our view very, very high and talk about path tracing. And I think this is the talk that wins the award for most amount of pictures and visualizations and least amount of text. But it's still deep path tracing, and I'll welcome Vladislav for the presentation. Yeah.
Thank you. Hello, everyone. Thanks for the introduction. I'm Vladislav from a small town of Bulgaria. I work at Chaos. I'm happy to present at GPC. Last year I was here as a spectator and I really liked the event, so I've decided to apply for a speaker this time. I'll be talking about the story of our company and how we've managed to get to the point to trace race in real time. And I'll dive in some technical details along the way. Hopefully this will be a light talk for the summary for the end of the conference. And I know that all of you are eager to get to the drinks afterwards. So let's begin. A few words about me. Computer graphics has been my passion since a little kid, and now I have more than 14 years of experience in the field. At the moment, I'm a development team lead, leading 3 teams, working on 4 projects, the main one of which is called Chaos Vantage, our real-time photorealistic ray tracing rendering engine. And I'm a part-time teacher working with students of all ages, from kids from the kindergarten all the way up to seasoned professionals. I'm teaching stuff related to computer science and graphics programming, of course. Let's start from the very beginning. Since the dawn of time, people like to spend their time nicely. Playing games, for example. We love to give life to our imagination. Enjoying and practicing sports is a big part of our everyday life. When computer came, everything changed. They gave us even more ways to enjoy our free time and work sometimes. Computer games were invented, and they became better and better throughout the years, challenging us in different ways, and at some point, even computer graphics was invented. Next, hardware graphics advancement was required to make even better games and other graphical applications, and the games evolved more rapidly, evolving year after year. For example, massive multiplayer online games connect the whole world digitally. The graphics hardware evolved also along the way, designed and created by different vendors like NVIDIA, AMD, Intel, and it seems that these devices won't stop to evolve ever soon. Thanks to them, the games evolved even further away, and they gave us even more epic ways to spend our free time. They are getting even really closer to the reality we live in. And computer graphics applies not only for games, of course. Thanks to it, epic and unforgettable 3D animated movies are created. Real-life action movies are enhanced with visual effects. Architectural visualization is also a big application of computer graphics. And now, what's our role in all of this? In our company, we create rendering engines with which our clients entertain their clients. And here I have some examples of stunning 3D scenes rendered with our rendering engines. Photorealism is a big part of computer graphics. We try to simulate our world digitally. And I'm happy to report that in our company, we've managed to achieve almost perfect photorealism. Thanks to our major product at the company, the offline CPU ray tracer V-Ray, we managed to create such images, to generate such images, simulating the physical light properties of the real world. And today I'll focus mainly on V-Ray and Chaos Vantage, 2 of our products, but we have a variety of a big portfolio of products. We have our hybrid rendering engine called Enscape, which is using rasterization and real time. We have Corona, which is another offline CPU ray tracer. We have our cloud asset library, and many more. We have tons of examples of our users achieving photorealism. This is another image generated by V-Ray for this human based on a 3D scene. And we have a customer which literally makes a living out of generating photorealistic portraits of his friends. This is a self-portrait of himself. The story for us began in March 2002. Back then, the first version of V-Ray was released, but there is a big backstory behind this. The company was founded in 1997 by Vlado Koilazov and Peter Mitev. Later in the years, Vlado even got recognized by an award of the Academy of Motion Pictures and Sciences for his work on V-Ray and the contribution of it to the movie industry. The first product of the company was released in 1998. It was called Phoenix. Unfortunately, it has nothing to do with our current version of Chaos Phoenix, the real a real fluid simulator. It was something like a simulator for environment effects. It used fractals and combining them using different curves. It got so popular back then, it even got used in the Diablo 2 cinematic trailers. The goal of our founders was to create as real fluid simulator as possible. And for this to happen, they needed good rendering technology. But unfortunately, back in the days, there wasn't such a technology, and the photorealism was far behind the track. And they've decided to fix this, and they created a rendering engine for their fluid simulator. And that's how our flagship product, V-Ray, was born. Now let's dive a bit more into the details for V-Ray. With V-Ray, we generate such photorealistic images, and for this task, a lot has to be considered. Gigantic meshes created by literally millions and billions of triangles have to be consumed by the renderer. These triangle meshes are representing the objects in the scene, like the car, the windmills behind the car, and the mountain. Complex white setups has to be simulated. Global illumination, indirect illumination, reflection, refractions has to look really good in the final image. Nice shadows also has to be computed, and many other things. We have complex material and texture networks that has to be evaluated, hardware utilization, and many more. The truth is that we are just simulating a physical camera in this digital 3D scene. Such scenes are prepared by 3D artists in dedicated programs, and V-Ray is a plugin, is distributed as a plugin for these platforms like 3D Studio Max, Autodesk, Maya, and so on. In these scenes, the designers are creating the objects, they set up the light sources, and probably the most important thing for us is where's the camera and how it's orientated to observe the 3D scene. Based on this information, we consume it, give it to V-Ray, run our algorithms, and calculate colors for all the pixels of the final frame that we want to generate. In order to do this, we have to simulate a lot of rays. We use rays to simulate the path of light photons, but we do it in reverse compared to the physical world. We shoot our rays and begin the path of photons from the camera position, trace them in the scene, and towards the light sources. So we have to trace millions and billions of rays, which is not a trivial task at all. And that's actually the path tracer. A path tracer follows the path from the camera towards the light sources in a 3D scene. Let's examine with a bit more details. This is a relatively simple 3D scene prepared by a talented 3D artist, a room, and a ball inside the room. As I said, all of the geometry in the scene is most often represented using triangles, but I won't show triangles in my examples today. These scenes live in the so-called world or global coordinate 3D system. The camera in this example is situated at the origin of the coordinate system, and it's looking towards the 3D objects. a unit away in front of the camera, we have a rectangle subdivided into smaller rectangles. Each small rectangle is representing a pixel of the final frame that we want to generate, and our path tracer has to calculate colors for all of the small rectangles, and each color calculated for a rectangle will be stored in the corresponding pixel of the final image. Next, we have to simulate these paths and trace them in the scene. The path is starting from the camera position, and we generate the so-called primary ray or the camera ray. It's shot towards the middle of the pixel, towards the middle of all pixels, but here we have a single ray towards the bottom row of the image. Okay, then we project this ray into the scene, and we iterate the triangles to find the closest intersection point to the ray origin along the line of the ray. Next, we have to compute the light contribution for the hit point, or we have to shade this hit point. In a scene, we could have several light sources. Here, I'm using these three spheres to illustrate 3-point light sources. And we have to calculate their contribution to the initial hit point by shooting secondary rays, called shadow rays very often, and they are directed from the initial hit point to the position of the light sources. The main job of these shadow rays is to calculate if a light is contributing to the hit point that we want to shade. In this example, the middle light source won't contribute much as the other two. Okay? In reality, we have to shoot many other rays after we find some hit point, and they are shot in a random position around the hit point based on the normal, the hit surface, the material, and so on and so forth. And we recursively trace all of the other rays in the scene, projecting them in the scene, calculating intersection points with the triangles, calculating direct illumination for the new hit points, and so on and so forth. And this is how we define a path in our path tracer. We start from the camera, hit something along the way, generate new rays, again hit something, and get to the light sources. This is another example of a light path, and a third one. Okay, and we have to do this for all camera rays, for all pixels. We have to generate the primary rays and then trace them in the scene. Initially, V-Ray started as a CPU-based ray tracer, offline ray tracer. Unfortunately, back in the days, there weren't good GPUs for general-purpose GPU programming. There weren't even good GPUs that did OpenGL. So, one of the most important jobs of V-Ray is to utilize the CPU power of the system on which it runs. And here I hopefully have a demonstration of how V-Ray is utilizing the Threadripper processor with 64 cores in this example. And I'm not sure if I mentioned that V-Ray is distributed as a plugin to these famous 3D applications. Here V-Ray is installed in 3ds Max, and when I start the video, you'll see how the cores of the processor are utilized. Yeah, almost perfect utilization, and here the idea is that the image is whoa, sorry about that. The idea here is that the image is subdivided into small regions called buckets, and each thread of the CPU is assigned a bucket, and it has to calculate colors for this bucket and save the colors in the final image that's generated. And bucket after bucket, the final image, the final photorealistic image, is generated. And at the end, even the buckets are subdivided further. Okay? Of course, we cannot rely entirely on the system on which our software runs, so we have to implement other optimizations. We have multiple important sampling, which tells us which are the most important rays that we have to trace. We have Russian roulette, which terminates our white path intelligently. We could guide our rays in the proper directions that are most important. Acceleration data structures are a big topic in ray tracing. and many other things could be done. Now let's focus our attention on the acceleration data structure, something that was heard throughout the conference this week a lot. I'll use this relatively simple scene and a custom CPU ray tracer that I've wrote for demonstrating this. Let's get back into the 3D space. The camera is again in the origin of the global coordinate system. The triangles are somewhere in a perpendicular plane to the z-axis. And then the other batch of the triangles is behind the first, ignoring the x-axis for convenience. Again, we have an image plane in front of the camera, and this image plane is for relatively small image of just 25 pixels, 5 by 5. We generate camera rays and shoot them in the scene, and we have to intersect all of the rays with all of the triangles in this scene. After rendering this, I get this image, which is really zoomed in, and I have some statistics. In each pixel, I write how many ray triangle intersections are performed. In the green pixels, where nothing is hit by the generated camera ray, we have only 8 triangle intersections. In the colored pixels where I have 16 triangle checks, I have shot a camera ray, intersected it with 8 triangles, and when an intersection is found, a shadow ray is shot towards the single light source in the scene, and that's why the 8 triangles are checked twice for intersections. Okay? Now, how we could improve this using acceleration structures. First, we have to build such an acceleration structure, and it will represent the 3D space of the system in an hierarchical intelligent structure. Okay, this is the scene, and we enclose all the triangles of the scene in the so-called axis-aligned bounding box. So this purple box here contains all the triangles of our 3D scene, and this box is stored in a node of a tree, which is representing our acceleration structure, of course, and then we continue to recursively subdivide and slice these spaces, producing new subspaces with planes perpendicular to the axis. First, we slice the root bounding box with a plane perpendicular to the x-axis, and this gives us 2 new subspaces represented by the cyan bounding box and the yellow bounding box. Each box here is containing half of the triangles of the original scene. Okay? And we continue this recursively, slicing the subspace for the cyan box. We get 2 new subspaces containing only a couple of triangles, slicing the brown box up there with a perpendicular axis, with a perpendicular plane to the z-axis. We end up with these 2 new red and green subspaces represented by axis-aligned bounding box. And in them, we have only 1 triangle, and I've defined my algorithm for building the acceleration structure to stop when maximum 1 triangle is contained in 1 bounding box. So these boxes here are representing the leaf nodes of my 3 data structure, acceleration structure. And the slicing backtracks and continues recursively. Okay? Next, after building this acceleration structure before the actual rendering starts, we have to use it when the rendering starts. And let's see how it works in our example. Now, when the rays are generated in the scene, they will be intersected first with the acceleration structure, not directly with all triangles in the scene. And let's concentrate on this single ray for the last pixel of the second row. Ignoring the z-axis for convenience again, let's see what's happening. First, we intersect the ray with the box that's stored in the root node of our acceleration structure. And of course, we see that it's intersected, so we have to open this box, see what children its node has, and check for intersection with the bounding boxes in the children nodes. And here we see that the cyan box is intersected, and we completely ignore the subspace represented by the yellow box, which is a big thing in ray tracing. We continue to check for ray tracing. The cyan box has 2 children nodes, which are containing the bounding boxes for the brown and yellow subspace, and the brown subspace has 2 new subspaces in it. We intersect the ray with both of them, and now when we open the red box, we see that there we have now a triangle, no other boxes. So this means that we have hit a leaf node, and we have to iterate the triangles in this leaf node. Only one triangle is hit here, and we have to open also the green box, which is intersected by the ray. Okay, now let's see how this works with a slightly more complex scene. Here, I have my favorite dragon in the center, in the origin of the coordinate system. The camera is somewhere up here, observing the dragon from above. And again, the same thing repeats. We have to generate camera rays towards the middle of the pixels of the image plane and intersect them with the scene. And of course, I won't intersect all of the rays with all of the triangles of the dragon. I will introduce a acceleration structure again. And in this relatively simple example, only these 6 rays will be intersected with the geometry of my scene. All other rays will be almost free. This is an example of the ray tracer that I wrote for the demonstration. You could imagine this ray tracer as a very simple version of V-Ray. It's a CPU ray tracer. And yeah, this is the generated image for this scene of 2 objects, around 4,000 triangles, 1 diffuse material, 4 white sources, which are point-wise sources around the dragon, and it's rendered in full HD resolution. I'll use this table to demonstrate the effect of different optimizations. First, I've rendered this scene without any optimization, and it was rendered for around 500 seconds. Next, of course, I wanted to utilize the CPU power of my system, and I've subdivided the image into regions and gave each region to the available threads of the CPU threads of my system, and this improved the rendering even further. Introducing buckets rendering, because with the normal region rendering, divergence could be introduced, and with buckets I have smaller regions, which are stored in a queue, and each thread accesses the queue, gets a bucket to render, to generate color for it, and stores the colors for this bucket in the final image. Okay, and this is repeat until there's something in the queue of buckets. Okay, next bounding box are introduced, and each object now has a bounding box. So when I intersect a ray with the scene, first I check if a bounding box of an object is intersected, and then iterate all triangles. And drum rolls, the best we could do for our probably the best thing that we could do for our CPU ray tracers and ray tracers as a whole is to introduce an acceleration structure. And here I've shown you how the KD acceleration tree is built and how it works. And of course, it introduces big improvement. The whole scene rendered under a second. And of course, a lot more things could be done for this relatively simple example, but I wanted to showcase the effect of acceleration structures. Okay, how we could further improve V-Ray and our ray tracing? Probably the best thing that we could do for our CPU ray tracers is to port them to GPU. Using general purpose GPU programming, we could map a lot of threads from the GPU to calculate colors for different pixels and making calculations for triangle intersections, for example. And the game gets more interesting when several GPUs are involved in rendering. And of course, V-Ray took advantage of this. When the graphics cards caught up, we've implemented the GPU version of V-Ray, and it was officially released around 2009. It was initially implemented using the CUDA toolkit for GPU programming. Later, it was ported to OpenCL. Now we have also Metal version of it, and also HIP version. And I've prepared a demo for this, for V-Ray GPU rendering of a frame. And here I'm using Afterburner to show you how we utilize also the GPU resources of the system. The system that I've used for the demo is having 4 RTX A6000 cards. And again, an offline ray tracing is performed. The cards are utilized very good. The image is subdivided into buckets, and each bucket is rendered on specific video card, on specific GPU. Okay? next stop in our journey is, of course, real-time. That's why we're all here for. The idea of real-time, as we know very well, is to produce frames really fast based on user input. And, of course, hardware accelerations were implemented for real-time, and thanks to rasterization hardware, we could render a lot of triangles and shade them for the games. The users of V-Ray also wanted fast feedback for their photorealistic final renderer. They don't want to wait 5 minutes to see their final image and to find that they did something wrong. They wanted real-time feedback. So the first thing that we try to do is to implement interactive rendering using the V-Ray CPU version. And I'll show you how V-Ray CPU interactive rendering works in this scene in 3ds Max. Starting the video, I render directly in the viewport of 3ds Max using V-Ray CPU. And we are getting closer and closer to real time, but of course this is not a game-like experience. We have some lag. When the scene is modified dynamically, it's not rendered with good quality. When the camera is still, the colors for the pixel are accumulated over time, and it clears out. But yeah, for dynamic scenes, it does not work. A lot of limitations we have here. Maybe the major one is that the data generated by the CPU ray tracer has to be passed to the GPU, and then the frame has to be displayed somehow in the viewport of the application. Here, the PCI express what the PCI is involved into sending stuff around, and these are all expensive operations. One of the purposes of V-Ray GPU is the GPU version of V-Ray was to give faster feedback to our users. And let's see the demo on the same scene that I've used for the CPU interactive rendering. And yeah, here we see better feedback on my RTX 4090. But still, we are far from game-like experience. And the main reason behind this is that V-Ray and V-Ray GPU were implemented as offline renderers, and they accumulate samples over time, and it doesn't make sense to use them for real time. Very big topic is ray tracing in real time. When I began working in computer graphics industry, this was some kind of a joke to use ray tracing in real time, and no one believed that it would be possible. So yeah, at some point, hardware acceleration for ray tracing became a big topic, and even at our company, we did our own experiments of hardware acceleration for ray tracing using field programmable gate arrays. We tried to design hardware exactly for ray tracing. But unfortunately, this project was cancelled, this effort was cancelled, and we couldn't succeed. But fortunately, other bigger companies succeeded on this road, and NVIDIA RTX was created and introduced, and it skyrocketed ray tracing in real time, thanks to a collaboration with Microsoft. DirectX provided access to the hardware accelerations for ray tracing, specifically by using the DirectX ray tracing API. And now, let's see what's happening under the hood of a video card when we use this hardware acceleration for ray tracing. Removing the hood, we see the PCB board of the video card. We have the GPU, some memory around it. Let's remove the cooling system and concentrate ourselves on the GPU. The GPU processors are a really complex network of wires and transistor and logical gates. Examining them would require a very good microscope. So let's use a more simplified diagram. And zooming a bit, we see a lot of repeated parts. We'll see how they work for our purposes, and let's concentrate on one of them. This is the so-called streaming multiprocessor, and it manages many CUDA cores or shading cores. But we are most interested in the so-called RT core. This is the hardware part inside the GPUs that is providing the hardware acceleration for our ray tracing. It builds and traverses the acceleration structures like the ones that I've showed you, and it also intersects. It has special instructions for intersection of rays and triangles. And thanks to DXR and other APIs, of course, we have access to this functionality. And of course, other vendors have also such hardware acceleration parts, but yeah, I use NVIDIA for illustration. In order for all of this to work, for our rays that we generate, the so-called ray tracing pipeline has to be executed. And let's quickly see how this works. First, we have to generate our rays. Then we have to traverse the acceleration structures, for our 3D scene. And at some point, if a check for intersection of array and triangle has to be performed, a special dedicated shader program, GPU shader program, could be executed, and we could provide such a program ourselves. Also, we could provide a ray generation shader program. If a hit is found, another special GPU shader program will be called. It's named AnyHit, and this repeats until there is something to traverse for the generated ray. At the end of the traversal of the acceleration structure, DXR will check if a hit is found. If we don't have a hit, Mesh shader will be invoked. If there is a hit, closest hit shader program will be invoked. And of course, thanks to the hardware acceleration in the GPUs, all of this is happening really, really fast. Let's return back to our 8 triangle example with the acceleration structure. Now this acceleration structure is built by DirectX and the GPUs, and when we trace rays, for all rays, this ray tracing pipeline is performed. First, the ray is generated, then the acceleration structure is traversed, going inside into the structure and its hierarchy. We traverse it and intersect the corresponding boxes and the triangles inside them. At some point, when an intersection has to be checked against triangle, the intersection shader is invoked, and then any hit shader, because here we have a hit with the triangle, and of course we have to check for intersection with the blue triangle. In this case, we don't have a hit with the blue triangle, so we exit the traversing of the acceleration structure. DirectX exits for us. At the end, we have found a hit, so the closest hit shader will be invoked, and we could calculate the color for this pixel, the corresponding pixel. And again, all geometry inside these subspaces is completely ignored. We could have here robots, cars, cities, buildings, and whatnot, but we intersect only two triangles at the end. Okay, and the streaming multiprocessors will be invoked to do this job. For these examples, only a small portion of them will be used to traverse the whole scene. Our project Lavina was released to the public, was shown to the public at the SIGGRAPH 2080 edition, and it used DXR for ray tracing. This was the first real-time ray tracer at our company, implemented in our company, and I'll show you the original demo, which was shown at SIGGRAPH 2018. It showcased how this really big and complex scene is rendered in real time using ray tracing. Of course, here a lot of things have to be further improved, but this scene is indeed really complex with literally billion of triangles. And here other stuff from DXR is used that I haven't explained. Here we have buses, twases, and whatnot. I intentionally didn't speed up the video, so you're able to observe how it actually works. And yeah, it was a big hit for us. It was nice first version, nice proof of concept, and the users really liked it and pushed us forward to complete the project. And yeah, this is a logo of our flagship product, V-Ray. rendered with Wavina with real-time ray tracing. Something unimaginable several years ago. Okay, let's continue. A couple of years later, using this rendering engine, we've integrated it in our product Vantage, and it was officially released to the public. In Vantage, we have UI and a viewport in which we see the results from our real-time rendering, and with the UI, the users could modify their scenes, and the scenes are created for V-Ray. And this is a demo where the user could examine different viewpoints in the scene, navigate in the scene like a 3D game, and receive instant feedback with almost perfect photorealistic quality. Also, some settings of the scene could be adjusted, and yeah, again, the feedback is pretty good. Again, something like this was unimaginable several years ago, and now it's on the desktops of the most designers. I have another demo where I show you how Vantage handles scenes with a really huge amount of white sources. And yeah, here again we see good photorealistic feedback. And at the end of the tour, I will show you how many white sources there are. Here we have also emissive materials and whatnot. Literally, hundreds or even thousands of white sources could be rendered nicely in real time. Okay, I think I'm good with the time. So yeah, for good or bad, nothing like this would be possible without pretty good denoising. As we know very well, when we purely ray trace rays in scene, we could end up with the so-called noise effects or pixels that couldn't be computed with enough calculations and the given time. So we return some constant color. And yeah, if we have enough time, our ray tracer will converge to a pretty good image, but unfortunately we don't have enough time, especially in real time. So we give the noisy image to the denoisers. The denoisers detect where we hadn't time for enough calculations, and they fix the colors in these spots and reduce the noise significantly. The main denoiser and upscaler that we're using is DOSS from NVIDIA, and I'll show you really quickly the pipeline for rendering a frame using DOSS. This is Vantage, and we have to update the viewport. We have a Windows handle for the viewport. It's given to a DirectX swap chain. The swap chain is managing two buffers behind the scene in the GPU memory, and we have to fill the front buffer with some details, some colors for our image. First, our ray tracing part of the pipeline is executed, and it produces different images with different data for the frame. We have depth, albedo, normals, and so on and so forth. Then the DOSS pass is executed, and the data from the ray tracing is given to DOSS. DOSS performs its magic. It upscales the image and denoises it pretty well. Then this image is passed further for some post-processing and combination stuff, and it's stored in the buffers of the swap chain. And of course, at the end, we have to present this to the user. At the end, I'll tell you that at our company, we believe a lot in good education, and we've created our own in-house initiative called Chaos Camp. And in it, we are teaching the students how to create their own rendering engines using ray tracing. We dive deeply into how GPUs are working. We have dedicated course on algorithms for computer graphics. And in the center of all this is C++. And all the courses, of course, are tailored towards our projects that we use at the company. And we have hired many people from these courses. That's all I have for you today. Thank you for the attention.
Thank you, Vladislav. That was really cool. So we will do a little bit of questions for this, but just after that, we will have we'll wrap up the conference and do a couple of outro things, and then the reception starts. Just so you know. So yeah, are there any questions while we load the outro? Oh, there's one question. Perfect. Oh, there it is.
Hi.
Hello.
Is it working? Yes. So, Uber shader or wavefront?
Wavefront.
And how does wavefront work for you in terms of performance and complexity and everything?
Yeah, this is an interesting question. V-Ray GPU, the GPU version of V-Ray is entirely written as a wavefront renderer, and it's doing pretty good, but it's targeted for offline rendering, where we could afford rendering many passes in order to clean up the image and accumulating samples along the way.
Any other questions?
Hi, thank you. So when do you decide to export the image? Because it can converge forever, so what's your limit?
So your question is how much time we give for the renderer to converge to a final image?
Yes, exactly. When do you say it's OK?
We have a bunch of UI controls that we expose to user, and he could tweak. We have some time for which the renderer could clean up the image, or we have some noise threshold settings that could be reached. And the short answer is that this is controlled by the user. But we have pretty good defaults depending on the rendered scene.
Thank you.
No more questions?
Here in the front.
Oh, there was. Oh.
So my question is a lot more general. Having started from offline and now having real-time functionality, is there anything that you feel people in the real-time world could maybe learn from what's happening in offline now that we're seeing more adoption of, say, path tracing in games?
Yeah, that's also a really nice question. And we had these constant discussions for real-time versus offline. And a colleague of us said that for the real-time projects, we shouldn't hire offline people because they always try to compute more arrays per pixel, accumulate them over time, and this does not work for real-time. So, yeah, the gap between offline and real-time is really huge, and it was really hard for us to come up with a good solution for Wavina. But I think we did it good. Of course, we had a lot of help from NVIDIA and DLSS, but in the beginning, we tried to implement it completely like an offline renderer, just with the hardware acceleration. But yeah, we could discuss this afterwards more deeply. Yeah.
Thank you. Thank you so much, Vladislav.
No problem.